Hello and welcome to this talk about the adoption and effectiveness of same-site cookies. This is a joint work with my advisor Giancarlo and myself Soheil, and we're both from CISPA, Germany. Browsers include cookies in HTTP requests regardless of their context, including cross-site requests. And this behavior is abused by a family of web attacks known as cross-site attacks, such as cross-site leaks or CSRF. Now, a long-known countermeasure to protect from these attacks is to limit the scope of cookies to a same-site context. One way to implement this solution is to rely on external components such as HTTP proxies or browser extensions, which limits their impact considerably because they are external. However, only recently, Google revamped the idea of same-site policies for cookies by implementing in Chrome the same-site cookie attribute. The same-site attribute defines the context in which browsers can include cookies using three predefined policies. First, we have the none policy, which means cookies are attached to all cross-site requests. Then on the other side of the spectrum, we have the strict policy, which means cookies are not attached to any cross-site request at all. And finally, in between, we have the lax policy, which says cookies are attached to some cross-site requests that are potentially safe, such as top-level navigational requests. And what happens if a cookie does not explicitly use one of these three policies? Well, in that case, browsers will use a default policy. And when Chrome initially added the support for SameSite, the default policy was none, but the ultimate goal was to gradually transition to a secure by default opt-out solution. So that's why Chrome started showing warning console messages in September 2019 that cookies will be defaulted to lax. The lax by default was then initially enforced in February 2020, where we had this transition from same-site equal none to same-site equal lax for cookies that miss an explicit same-site attribute. Soon after, in April, this change was reverted due to COVID-19 pandemic and then reinforced in Chrome 84 as of July 2020. So since then, we have lax by default as the new default policy in Chromium-based browsers. And the question is how effective it is to mitigate cross-site attacks. More concretely, in this paper, we want to study the state of same-site policies adoption and the effectiveness of the new lax by default policy. Specifically, one of the first questions we intended to answer was how websites adopted one of the three same-site policies across the two lax by default rollout dates. Then, as we now have a new default policy, the second obvious question is what would be the cost of this change? What functionalities are broken? Third, we look at its benefits, that is how adequate and effective is lax by default to prevent cross-site attacks, and what are the threats to its effectiveness. And finally, we have a look at browser policy inconsistencies with respect to the RFC for same-site cookies, as well as the web framework default behaviors as they can revert the browser's lax by default protection. Starting with the first research question, we conducted a longitudinal analysis of same-site adoption on Alexa 500,000 sites, where we performed 8 crawls on Internet Archive from June 2019 to March 2021 with a 3-month interval between the crawls. And we found that around 18.9% of the sites adopted a valid policy, of which 3.7% disabled the same-site protection using the none policy, and the rest rely on stricter policies like lax and strict. Interestingly, we observed that the fraction of sites using the none policy increases with sites' popularity to up to 18% within the top 1K ranking. When looking at the trend of same-site adoption, the two lax by default rollout dates R1 and R2 in the figure seem to have played a relevant role with a steep increase of all same-site policies. That is a 7-fold increase in lax, a 4-fold increase in strict, and for the none policy, we observe at least a 20-fold growth with even more increase in more popular sites. Overall, after a rapid increment of sites using one of the same-site policies around the enforcement days, we now observe a rather moderate yet steady growth. Then a small yet non-negligible fraction of sites set an invalid policy, such as same-site equal 1, which is a string that does not match any of the 3 known policies. Invalid policies should be treated as the none policy by web browsers according to RFC 6265 BIS specification. As such, when developers make mistakes and use non-existing policies, this inadvertently could result in deploying a different policy than the intended one. Finally, for the remaining 80% of sites, our crawling did not observe an explicit policy, meaning that they may rely on the default browser behavior, for which we now have the new lax by default. Coming to the second research question, let's now have a look at the functionality breakage. So websites use cross-site requests for various functionalities, such as social media share and like buttons, advertising, and the question is what functionality are affected by the new default policy. To answer this question, we created a crawler based on Puppeteer and Chrome DevTools protocol and instantiated it with Alexa top 500 sites and a set of login scripts that we manually created for each site. The crawler relies on the pre-SameSite version of Chrome, which warns via CDP audits when a cookie that does not have an explicit SameSite policy is attached to a cross-site request, thus potentially breaking after the enforcement of the lax by default, and our crawler collects these requests. Then we determine the types of third-party functionalities affected by querying the request URL via the URL categorization services, such as the WebShrinker API, as well as the AdBlock EasyList, HostBlock and HostBlockList to account for the short-lived continuously changing advertisement domains. Finally, we determine the exact functionality affected for a random subset and confirm breakage when cookies are moved. Now, we performed the steps before the lax by default rollout. However, after the rollout, we revisit the affected request to confirm whether the new policy has indeed broken the functionality. So in total, our crawling identified around 9K URLs in 211 sites of Alexa Top 500 that supported the login feature. And in these URLs, the crawler collected around 22.9K cross-site requests without the SameSite cookie flag that are potentially affected. The URL categorization for these requests resulted in identification of 32 different types of affected third-party functionalities, such as technology in computing services like file sharing or live chat, and business services like advertising and analytics. And most importantly, our breakage experiments revealed that functionalities implemented by 19% of the affected requests are broken, which affects 17.5% of the sites. Then, interestingly, the majority of these broken requests, that is 77%, belong to online ads and user tracking functionalities. Coming to our third research question, we intended to study how adequate and effective are SameSite cookies to prevent cross-site attacks. Accordingly, we systematically reviewed existing literature for threats against SameSite cookies that enable cross-site attacks. Then we determined the threat severity by quantifying their prevalence in the wild. Overall, our systematic review identified 7 threats, and we also proposed 3 new threats, and we can divide these 10 threats into 2 categories. First, we have the threats leveraging cross-site requests not covered by the lax policy, and second, threats that are that use cross-site requests that are covered and protected by lax, but this protection can be bypassed due to developers' mistakes. Examples for the first category are applying state-changing GET requests for CSRF or abusing window properties side channels for information leakage. And examples for the second category are forging state-changing post requests for CSRF or SameSite intro or interpage inconsistency. Now, these are only some of the threats that I will exemplify in this presentation. However, please refer to our paper for more information about the remaining 5 threats not in this presentation. So let's have a look at the first threat. We know that top-level GET requests are not covered by the lax policy, and developers may misuse GET requests to implement security-sensitive state-changing operations, such as removing the resource. As such, attackers can obtain CSRF by replaying state-changing GET requests, for example, by abusing the window.open JavaScript API. Now, to quantify the fraction of state-changing requests that are GET-based, we crawled the Alexa top 1000 sites, identifying 42.5K URLs. Then we located all the HTML forms with a CSRF token, which is an indication that the operation of the form is state changing. And then we check if the request method in the form is GET. Accordingly, we determined the lower bound for GET-based state changes. Finally, we examined the correctness of the CSRF verification for a random subset of the requests. So in total, our analysis identified 6.9K state-changing requests, and we observed that 10.3% of them are GET-based within 88 applications. We discovered that 2.6% of the GET-based requests are forgeable due to faulty CSRF token verification, which affects popular sites like Pixiv and MailChimp, where attackers can delete user sketches or change user settings, respectively. Another threat is forging post requests with GET to bypass the lax protection. So again, assume that we have the two sites, attack.com and target.com, and the attack page sends a post request to the target site. And because of the lax by default, the browser will not include the cookie in this request. And even if it did, because the web application checks the CSRF tokens for the post request, which in this case is a false token F, the web app will reject the request correctly with a 404 status code. However, if now the attacker submits the same request with a different HTTP verb that is GET, then the browser will include the lax cookie in the request. And additionally, this web app only verifies CSRF tokens for post request. Thus, the attacker achieves a successful CSRF. Now, to quantify the prevalence of this issue, we used our previous dataset of the crowd of Alexa top 1K sites, and then selected one random request for each post request in the dataset, and we checked its susceptibility to CSRF by replaying the request using a different HTTP method, that is GET. So in total, we discovered that around 1.5% of the state ranging post requests are forgeable with GET, compromising the database integrity in popular web applications like MDB and Meetup. Also, in this paper, we proposed 3 new threats that are caused by developers' mistakes and can downgrade the SameSite policy. The first issue is SameSite cookie intra-page inconsistency, and it arises when web applications set redundant cookies to support incompatible clients, but these cookies have different SameSite policies. For example, here we have the CCC legacy cookie without the SameSite attribute for incompatible clients, and then CCC cookie with SameSite equals strict for modern clients. For a victim visiting a CSRF attack page using the modern browser, the CCC cookie is never sent to the target site, but the CCC legacy is bypassing the SameSite policy. This issue affects around 1.4% of the top 500 sites, such as GitHub, CNN, and Yahoo. Another similar threat is SameSite cookie interpage inconsistency, which arises when the web app sets 2 different policies for the same cookie across 2 different web pages. And this issue affects 3.3% of the top 500 sites, such as AliExpress and Vimeo. And the last issue is SameSite cookie user agent inconsistency, which arises when the web app sets 2 different policies for cookies based on the incoming request user agent, for example, mobile versus desktop. And this vulnerability affects 1.8% of the Alexa 500,000 sites, 138 of which are within the top 1K ranking. Okay, so these were only some examples of the threats and measurements in the paper. But the point is, what did we learn from our experiments about the adequacy of SameSite cookies? So when looking at the cross-site request context, we have the contexts that are protected by SameSite policies like LAX, and the contexts that are used for security-sensitive operations in web applications. And the great thing about SameSite cookies is that they significantly reduce the attack surface for cross-site attacks, which is fantastic. However, as we have demonstrated, there is a mismatch between cross-site request contexts covered by LAX and the ones used by websites to implement security-sensitive operations. Finally, even when using LAX to restrict policies, much of their effectiveness depends on developers who may introduce inconsistent or conflicting policies, leading to SameSite policy bypasses. And in this complex landscape, we also need to factor in corner case inconsistent behaviors of browsers and web frameworks. In particular, our analysis of 14 different browsers revealed that they exhibit 7 divergent behaviors with respect to the SameSite policy. For instance, when we have SameSite equal invalid or SameSite equal non-cookies without a secure flag. Now, for timing reasons, please refer to the paper for the individual browser behaviors. But the point is, as of today, web application developers need to be aware of all these 7 behaviors if they want their website to work with all these browsers and provide the same security guarantees. And one way to achieve that is using user agent dependent SameSite policies, but as we have demonstrated, header inconsistencies can be the root cause of vulnerabilities. Finally, even when browsers enforce a default LAX policy, web frameworks built in APIs can downgrade it to none by default. Specifically, we analyzed the top 5 frameworks of top 5 web programming languages and observed that 24% of them revert the LAX by default protection by implicitly setting a non-policy when the developer uses the framework set cookie built-in APIs. Again, for more information, please refer to the paper. In summary, in this paper, we first studied the adoption of SameSite cookies, measuring how website developers adapted to the new LAX by default policy. Then we showed that functionalities implemented by 19% of the affected requests are broken, the majority of which are for online ads. Third, we quantified the fraction of the attack surface not protected by lags by default and showed that there is a significant mismatch between request context protected by lags and the context used by websites to implement security-sensitive operations. And finally, we showed that browsers diverge when enforcing the SameSite cookie policy, and 24% of the top 25 frameworks can revert the lags by default protection when the developer uses the framework's built-in APIs. And with this, I would like to conclude my talk. Thanks a lot for your attention. And if you have any questions, please don't hesitate to ask.
Thanks for the talk. Questions?
You mentioned that, first of all, Omar University of Washington, nice talk. I really learned a lot. My question is about breakage. You mentioned that in some cases, the SameSite policy causes breakage. Do you have any idea of how much breakage there is? And what do you mean by breakage? Does it mean that the website is unusable or some content is missing, but the major functionality is still accessible?
Yes, great question indeed. Basically, what we observed was that 19% of the affected functionalities are essentially broken, and broken in the sense that the functionality does not work. They have service discontinuity. So, for example, to give a concrete example, are single sign-on implementations. So, for example, websites use single sign-on frameworks like OpenID Connect or SAML, who basically try to optimize user experience by including session cookies when you want to re-authenticate to the cookie. So if you already have a cookie and it is valid, they basically want to optimize the user experience by including the cookie. And these communications are essentially typically implemented via cross-site post requests, such as cross-site post forms or asynchronous post requests. And because of the new lags by default policy, these cookies will not be attached to these request contexts. Thus, single sign-on will not work, for instance.
Right, and you mentioned a lot of breakage is specific to advertising and tracking services. Do you have